Well, before we plow full speed ahead into methods for dealing with second-order equations, let's note that sometimes, under special circumstances, a second-order equation can be reduced to a first-order equation. And then we can employ methods learned to deal with those in order to solve the second-order equation. In this video, we give two examples. Here's the first example. So this is the case when y is missing. So y is missing, and that means in this particular instance that our second-order equation looks like y prime is a function of t and y prime. No y on the right-hand side. Here's what we can do. We can set u equal to y prime. Y prime. If we do that, then what happens to our equation? Then u prime, which is y double prime, is then equal to f of t y prime. And since y prime equals u, this is f of tu. And now we have a first-order equation in u as an unknown function of t. If we can solve it, so solve it if we can, it will involve one single unknown or general constant, since it's a first-order equation. If we can solve it, then we can just set y equal to the antiderivative of u, and again another constant will come in, and that will be a solution to our original differential equation. Note there are two arbitrary constants, the c here and the constant implicit in solving this equation. Okay, now let's illustrate with an example. So here comes an example. Y double prime plus t times y prime quantity squared equals to 0. Clearly a second-order equation, a term in t, a term in y prime, but no y. Y is missing. So y is missing. And so therefore, the method just outlined should work. We set u equal to y prime. And then our differential equation just becomes u prime plus t u squared equals 0. A first-order equation in u. We can solve that equation. It's not linear because of the u squared, but the variables are separable. And so if we separate them, we get the equation du over u squared equals minus dt, t dt. It's t dt. Okay, and now we integrate both sides. So let's do that. We integrate both sides. And now I'm running out of paper, so let's go to the next screen. Okay, resuming, I've written the differential equation again over here. The substitution was u equal y prime, and we had arrived at this integral equation, both sides of which we can integrate rather easily. Left-hand side is just minus 1 over u, and the right-hand side is equal to minus t squared over 2 plus a constant of integration. Let us call it c. Sorry, it's minus 1 over u, not minus 1 over u squared. And that equation is rather easy to solve for u. If you do that, you get u is equal to 2 divided by t squared minus 2c. And I'll just call that minus 2c c1, so let's write this as 2 over t squared plus c1. Now, we then have to integrate that function, and it matters what the sign of c1 is. In fact, there are three cases. if c1 is equal to 0, then y, which is the antiderivative of u, is nothing more than minus 2 over t. On the other hand, if c1 is a positive number, and you anti-differentiate, then you get the following expression. You get 2 over k times the arctangent of t over k plus another constant of integration, c2. I should have written that up here too, plus c2. And k here is the square root of c1. And finally, if c1 is negative, then y turns out to be 1 over k times the logarithm of the following quotient, k minus t over k plus t. And again, there's a constant of integration, c2, and k this time is the square root of minus c1. So that's very nice, starting with this differential equation here, in which the term y is missing. We were able to find lots of solutions for this second order equation involving two parameters. But there are two interesting observations to make. The first is that we have not found a single formula for a general solution of the original equation, and that's quite typical of nonlinear equations. And the second interesting observation is that although we found lots of solutions, we in fact have not found them all. Here is another one. Y equals C2. If y is any constant, then its second derivative is 0, its first derivative is 0, and so that function solves the differential equation. So now we found all the solutions of the second order equation using a method of reducing the second order equation to a first order equation. Let's look at a second instance in which we can actually do this. So here is the second example. That's when t is missing. Okay, in that case, the second order equation just becomes y double prime equals f of y, y prime. No t on the right-hand side. So how do we deal with such a situation? We set v equals y prime. Then what happens? Y double prime is just v prime. V prime is f of y. Again, y prime is v. So now we apparently have a first order equation in v as an unknown function of y. The problem is this is dv dt, not dv dy. So in order to recast it in that form, we have to use the chain rule. The chain rule tells us that dv dt is equal to dv dy, dy dt, and dy dt is just v, so this is v dv dy. Okay, and that's supposed to be equal to f of yv. And now we have a first order equation in v as an unknown function of y. So we try to solve it. If you can, then you can proceed as follows. Let's suppose that the solution is something function v equal phi of y. Then we are now reduced to the equation v equals the y dt equals phi of y. That's now a first order equation in y as an unknown function of t, and we can solve it in principle because it is separable. Okay, so that's the method. In the two steps involved, in each of them, in the solution of this equation and in the solution of this equation, arbitrary constants will be introduced, and so again there will be two arbitrary constants, as one expects when one solves a second order equation. So there's the method in the case that t is missing, and now let's apply it to an example. Okay, here's the example. The equation is y double prime minus 3y squared equals 0. And in this case, let's actually do an initial value problem. So let's take y of 0 equal 2, y prime of 0 equals 4. So notice that there's no t in the second order equation, so the method should apply, and we'll actually get an explicit concrete solution for this initial value problem by setting v equal y prime, and then noting that, as we saw on the last screen, y double prime is v dv dy, and so that equals 3y squared, and as predicted we get a separable equation. So separate the variables. V dv is 3y squared dy. Integrate the equation then, and we get v squared over 2 is equal to y cubed plus a constant. And now use the initial data, y prime 0, or v of 0 equal 4. And so if you do that, you get 4 squared over 2 equals 2 cubed, because y of 0 is 2, plus c. So c is 0, because this is 8 and this is 8. C is 0. So our equation now becomes v squared is equal to 2y cubed. And so v is equal to plus or minus square root of 2y to the 3 halves. And again, the initial data forces the plus sign by the initial data. And so we get the equation. And remember that v is dy dt. So now we have dy dt is the square root of 2y to the 3 halves. Again, we can solve that problem by separation of variables. So variables are separable, and a little bit of calculus leads you to the square root of 2t equals minus 2y to the minus 1/2 plus a constant, let's say c2. And again, you use the initial data, and you find that c2 is the square root of 2. Okay, then a little bit more algebra is required to solve for y. If you do that, you get that y is equal to 2 over the quantity 1 minus t squared. So that's the unique function which solves this differential equation and these two pieces of initial data. You notice that that's a perfectly good function for t less than 1 containing the point t equals 0. So we have got our second example, and we've now provided you with two instances in which a second order equation can be reduced to a first order equation. There was some hypothesis required in order for that to be achieved, and for a general second order equation we of course cannot do that. But this technique is useful, and it harkens to a technique that we will see later in the course, the so-called method of reduction of order, which will be a method of dealing with second-order linear equations later on, again in which one reduces a second-order equation to a first-order equation.